We are going to solve a problem on deviations from ideal bond angles defined by the valence electron theory. But before we do that, let's review some of the basic concepts. So deviations from the bond angles are going to be caused by electrostatic repulsion, caused by electron groups on single bonds. The electron groups that could cause this repulsion would be a lone pair of electrons, such as that illustrated in this orbital representation of this V-shaped molecule, triple bonds, double bonds, and all of these electron groups have a stronger electrostatic interaction than a single bond in the order in which appear here. The strongest one would be the lone pair of electrons, followed by triple bonds, followed by double bonds. The V-shaped molecular structure that we have here, also known as the bend shape, have a molecular geometry of AX2E. E represents a lone pair of electrons. We can see that there are two bonds here, and that the angle that ideally should be 120 degrees between the two bonds is reduced, is less than 120 degrees because of the repulsion that these bonds experience caused by the lone pair of electrons. Another example of this is when we have a tetrahedral geometry of the electron configuration. Here we have another example in which the shape of the molecule is V-shaped or bent. The molecular geometry is an AX2, E2. It is E2 because it has two lone pair of electrons, as we can see in this diagram. And because these two pair of electrons are also causing repulsion of the bonds, the angle, the ideal angle of the tetrahedron is 109.5 degrees. It's going to be much less when we have this repulsion from the lone pair of electrons. Another example is seen here, in which we have a trigonal bipyramidal electron group configuration. The molecular shape that we have here is an AX4E, meaning that we have 4 bonded atoms and one single pair of electrons, and that this single pair of electrons is causing repulsion to the multiple bonds that we have here, multiple single bonds that we have here. So we have 4 bonds. The angles between those atoms bonded on the axial direction, following the cursor here, are going to be less than 90 degrees with respect to the other angles of the bonds on the equatorial position. And the angles that are on the equatorial position are going to be less than 120 degrees between the two atoms that are being indicated by the cursor, because again the repulsion of the single bond of electrons. The last example represents this octahedral configuration. The molecular shape is the square pyramidal, or AX5E. We have 5 bonds here, 5 bonded atoms, and the angles, the ideal angles for all of these between the different bonds should be 90 degrees. But because of the repulsion of the lone pair of electrons, these angles are going to be less than 90 degrees. So now that we have reviewed these concepts, let's go ahead and try to solve a problem that deals with the issue of non-ideal bond angles. The problem reads, assuming that we have different species, A, Fn, A meaning a central atom and F being fluorine atoms, N meaning the number of atoms, let's order of increasing bond angles these particular compounds, BF3, BF2, CF4, NH, NF3, and OF2. Please take a few minutes to think about the solution, work the solution, and then let's compare our answers. To solve this problem, the first step is going to be draw a Lewis structure for each of the different species. We are going to apply then the valence shell electron pair repulsion theory to define molecular type and the location of the lone pairs of electrons, which are going to be important to define the the non-ideality of the ideal bond angles. Then we're going to identify single bonds that are perturbed by the lone pair of electrons. And finally, we are going to assign angles, ideal or modified, and rank the different structures according to their modified or ideal angles. So let's work on the first structure, BF3. BF3 will have 24 electrons. That is, it has 3 times 7 electrons for fluorine, plus 3 for boron, which is 24 electrons. We can draw the structure for this, the Lewis structure for this compound, and we're going to place the electrons on the most electronegative atoms. So that's, and we have 18 electrons for the for non-bonding electrons and 6 for the bonds, so that's 24. This configuration corresponds to an AX3 molecular shape, and the angles between the different bonds would be 120 degrees. Let's work on the next structure, which is BEF2. This one has 2 times 7 atoms of fluorine plus 2 electrons for beryllium. That's 16 electrons, valence electrons. We are going to have 4 for bonding and then 12 for non-bonding. We're going to put 6 on each fluorine atom. And this type of molecule has the molecular geometry of AX2. And the angle between the bonds is 180 degrees. Let's work on the next molecule. The next molecule is CF4. We have 4 fluorine atoms, 7 electrons each, plus 4 for carbon, a total of 32 electrons. Place carbon in the center, and then we're going to have a tetrahedral arrangement of fluorine atoms around it. So we have a total of 4 bonds, so that's 8 electrons. We have a total of 24 electrons that need to be placed. And we're going to put 6 electrons on each fluorine. And that basically gives us a molecular geometry of AX4. And the angle between bonds is 109.5 degrees. The next structure will be that of NF3 that has a total of 3 times 7 plus 5, which is 26 electrons. We are going to put nitrogen in the center, fluorine atoms connected to the nitrogen. We have 3 bonds, so that's 6 electrons, and we have to place 20 more electrons. So we place 6 on each fluorine atom. That's 18, and 2 on the nitrogen. So this molecule will have the shape AX3E because we have 1 lone pair. That lone pair causes repulsion towards the other bonds. So the angle is going to have to be less than 109.5 degrees. The last structure of interest is that of OF2. So OF2 has 2 times 7 plus 6 That's 20 electrons. Central atom is oxygen. And we're going to have then to play, we have 2 bonds, so that's 4 electrons. We have 16 electrons to place. So we are going to place 6 on each fluorine and 2 lone pairs on oxygen. Because there are 2 lone pairs on oxygen, we have an AX2 E2 molecular shape, and the repulsion of 2 pairs of molecular oxygen is much more than 1 lone pair of electrons. So therefore, the bond is going to be much less than 109.5 degrees. In summary then, we can see that the smallest angle will be that of OF2, then we're going to be followed by NF3. Then it's going to be that of CF4, followed by that of BF3. And lastly, the one that has the largest angle will be BEF2.